Hey everybody, Dr. Retzik here with you. This is our fourth video in Math 406. We're still in section 6a. We're starting to see a structure emerging from our inner product on our vector space. And that structure is a geometrical thing that has a lot to do with the norm. So we're still in 6a. This is section 6a continued. And what we want to do today is establish two important theorems that are geometrical in nature. Okay, so to get the ball rolling, we got to remember where everything stands right now. And in particular, we have to think about that orthogonal decomposition. So there's this picture. It's a Calc 3 picture, but it serves as our model for what's happening here in the more abstract setting of an inner product space. So this is our model, and I just want to draw it because we're going to refer back to it over and over again. Here's the model. You got a vector u, you got a vector v. You think of the vector u as consisting of two pieces. One of its components is that green vector. The other of its components is this red vector. And the green vector we've actually identified. That green vector is some multiple of v. It's not v itself, but it's a multiple of v. And we could even write down what that multiple is. That green vector is nothing other than u inner product with v over norm v squared all times v itself. So in the parentheses is just a scalar, and we're scaling that vector v by that amount. And for today's discussion, we're just going to have the third leg of that triangle, the red vector. Let's just call that w. And so what we've done here, excuse me, is we've taken u and we've expressed it as a sum. We've decomposed it. We've broken it down into a sum here where u equals the green thing. So inner product uv over norm v squared all times v plus w. And the key thing there is that this piece, the w, this piece is orthogonal to v, and therefore also orthogonal to the green piece, because the green piece is just a scalar multiple of v. This is our model. We have a way to take any two vectors and decompose one of them into this orthogonal decomposition with respect to the other one. Okay, and that's going to purchase us a lot. And right now, at this very moment, it's going to purchase us the big theorem of section 6a. Okay, here we go. Theorem. This one, we will get a lot of mileage out of this theorem. This theorem is called the Cauchy Schwarz theorem. And here's what it says. Let V be an inner product space for each u and v belonging to v. The size of the inner product So that's regular old absolute value bars. Remember, the inner product is a scalar. The absolute value of the inner product is no more than the product of the norms. And this is true in utter generality in any inner product space. Okay, this one we should definitely prove. The proof actually has added value in it. You get sort of additional statements to the theorem from observing the proof. Okay, so let's get a new sheet. And let's see if we can prove this thing. Okay. Easy first case. If v happens to be the zero vector, then we're done before we start, because both sides of the inequality up here, both sides of that are 0. So if v is the zero vector, we're done. So let's just assume v is non-zero for the rest of it. So let u and v belong to big V with little v not the zero vector. Okay, well, the key insight is our orthogonal decomposition. If we decompose u equal to inner product of uv over norm v squared, all times v plus w, where w is orthogonal to v, then we can talk about the square of the norm of u. By Pythagorean theorem, since u is a sum of two vectors that are orthogonal to one another, the square of the norm of u is nothing other than the square of the norm of the first vector, which is inner product uv divided by norm v squared. Note, dividing by norm v squared is legit here because we're assuming v is non-zero. Plus the square of the norm of w. That equal sign right there, this is key. Make sure you're clear on why this equal sign is legit. This equal sign is Pythagorean theorem. Remember, u is a sum of two orthogonal vectors. Okay, let's keep going and try to work this out a little bit here and see what this actually is telling us. All right, key thing, look at this expression. The stuff in the parentheses right here, that's a scalar. That's just some number. And we know that in general, if you're interested in the norm of lambda times v, that's the absolute value of lambda times the norm of v. We touched on that. Kendall pointed that out actually in yesterday's class discussion. You can just like factor stuff out of the norm, where stuff means scalars. In any case, that mess inside the parentheses is just some number. So pull that out of the norm, bearing in mind that it's norm squared. And I think what we'll have is absolute value inner product uv squared over what? Norm v squared squared, so norm v to the fourth. And after we've pulled out that scalar in front of that first norm squared, all that's left inside is v. And we didn't really do anything to the whole w piece of the expression. So I think we're there. Okay, now clearly that first piece cleans up a little bit. Furthermore, look at this. Norms are always bigger than or equal to 0. So this piece right here makes that line at least as big as what it would be if it weren't there, because the square of the norm is bigger than or equal to 0. So we can cancel what? Here and here makes a 2. And so finally, we're all the way down to here. Absolute value of uv, inner product, all squared, over norm v squared. Okay, look what we got here. Look at the side we started with. That's this. And that's bigger than or equal to all this. If you clear that fraction, I think you're done. You're there. Thus, the square of the absolute value of the inner product of u with v is indeed less than or equal to norm u squared times norm v squared. Now we can just take square roots, and we have the statement of the theorem. So that's the end of the proof. All we have to do is take square roots at this point, so I'm going to call it done. But I want us to get some added value out of this proof. Not only is the inequality always true, we've established that by way of orthogonal decomposition and Pythagorean theorem. Not only is the inequality always true, but think about the only way this could possibly come out to equality. Look back in the proof. In particular, this move here. The only way that inequality is an equality is if W is norm 0. In other words, if W is 0. And if W is 0, then U was a multiple of V in the first place. This is an important addendum to the statement of the theorem, and the reason that space was left at the bottom. Not only is the inequality always true, but we also, from the proof itself, we can see, moreover, it's an equality if and only if W was 0 in that orthogonal decomposition. In other words, if and only if U is a scalar multiple of V. So that's the full statement of Cauchy Schwarz. You get the inequality anytime you want. The inequality happens to be an actual equality precisely when U is already some scalar multiple of V. And you even know the scalar multiple. The scalar multiple is given down here, right here, in that orthogonal decomposition. So this Cauchy Schwarz theorem, this is rich with information. And I don't want you guys to forget that second bit of the theorem. The only way it turns out equals is if U was already a multiple of V. Okay, this is a big moment for us. Having this Cauchy Schwarz is very powerful, and I think is really the only thing beyond our discussion from Friday that you need to be equipped with to do all of the weekly homework. So now that you have Cauchy Schwarz, I think you're in the game on every single one of those weekly homework problems. Before we leave today's video, let's do a nice little theorem that follows from Cauchy Schwarz. And this theorem, this is an old classic. You guys know this. as triangle inequality. So as our last order of business today, let's think about this theorem called triangle inequality. Now they call it this because you guys know it in a very geometrical sense, that the longest leg of a triangle is shorter than the sum of the lengths of the other two legs, or like shortest distance between 2 points is a straight line. So on any triangle, the length of the longest side is shorter than the sums of the lengths of the other two sides. That's how we think about it in a non-fancy, non-college math kind of way. But it extends into this setting. That geometrical notion extends into this setting where you just have an abstract inner product that induces a norm. That triangle inequality statement still holds true. So the statement goes like this. Let big V be an inner product space for any U and V that belong to big V the norm of U plus V is less than or equal to the norm of U plus the norm of V. So that inequality there people call the triangle inequality, and it's wildly important in all sorts of branches of mathematics, and in particular right here as we study inner product spaces. The proof is really just a corollary of Cauchy Schwarz. So let's see if we can prove this thing. This proof, this is one of those kinds where you start with the left-hand side and you just write down what it means, and you do some stuff and you do some stuff and you do some stuff, and then eventually you find out it's less than or equal to the right-hand side. So it's kind of one of those follow your nose sorts of proofs. So let's just let U and V belong to big V. And let's start looking at the left-hand side. Now, here's a pro tip. When you're trying to make some statement about the norm of some vector, it's often easier to look at the square of the norm of that vector, purchase some statement about the square of the norm of it, like say you find out that the norm of W squared is less than or equal to 25. Well, then that tells you that the norm of W is less than or equal to 5. So we're going to work with squares. So start with the square of the left-hand side. And you guys know, by the very definition of the norm, that's nothing other than U plus V inner product with itself. Which we know because of additivity in the first and second slots. We're free to, quote, FOIL. So just FOIL that thing out. So you get, U with U plus U with V plus V with U plus V with V. Okay, so that first term there, that's just the norm of U squared, which we're happy to see because that's kind of one of the ingredients on the right-hand side of the thing we're trying to prove. And then this last term here, that's norm of V squared, also happy to see that. These middle terms, now we don't know anything about those. There is no hypothesis in place here about U and V being orthogonal. We really don't know anything about these middle terms. But I know this much. I know that VU inner product is the conjugate of UV inner product. So those middle terms are the complex number U inner product V plus its conjugate. So those middle terms are nothing other than twice the real part of whatever the inner product of u with v is. That move right there, don't zone out on this. It's not that bad. Inner product of uv is just some complex number. If you add a complex number and its conjugate, like a plus bi plus a minus bi, the imaginary parts go away and you just get twice the real part, 2a. So that's all that happened right there. Okay, so there we are. All right, fine. Now, here's the thing. Next move. The previous line is less than or equal to this quantity. What we're going to do is think about a complex number, 5 plus 3i. The absolute value of 5 plus 3i is square root of 5 squared plus 9 squared. And in particular, for any complex number whatsoever, the real part of that complex number is no bigger than the absolute value of that complex number. So for 5 plus 3i, 5 is definitely no more than root 5 squared plus 3 squared. And it's important in this line because we're going to trade in real part of the complex number u inner product v for absolute value of the inner product u with v. So the previous line is less than or equal to norm u squared plus twice absolute inner product u with v plus norm v squared. Now we're going to use Cauchy Schwarz because we know the absolute value of the inner product of u with v is less than or equal to norm u, norm v, and now that mass factors as norm u plus norm v all squared. Thus, we've done it. Hooray. Thus, the far left-hand side of that whole giant expression up there is less than or equal to the final bottom expression. And apart from taking square roots, that's exactly what we hoped to prove. So we're done, and the triangle inequality is true. Okay. Just as with the proof of Cauchy Schwarz, there is added value in observing something about the proof of triangle inequality. Look right in here. The only way you get an equal sign in triangle inequality is if you have an equal sign right here. And you already know when you have an equal sign in Cauchy Schwarz. So I'm going to leave it up to you guys to think about the exact conditions under which you get an equal sign in triangle inequality. But the clue is in the proof itself. All right. A couple other nice geometrical things follow from this. You can read about those in section 6a. There's something called the parallelogram law. But really, the two big takeaways here are Cauchy Schwarz and triangle inequality. And you definitely have enough to tackle that weekly homework now. And I think we'll leave it at that. Next video coming up is going to be for Tuesday. and it's going to sort of take us back into a more Math 306 mindset in this new setting. All right, see you later. Bye.